Now we discuss the differential analysis of fluid flow, and really this is the main source of fluid flow governing equations that exist and that are taken to be to solve all problems that are related to fluid flow. Whatever we have discussed and whatever problems occur, in fact, what we call as Navier-Stokes equation, they are supposed to govern generally a generalized form of equations of fluid flow motion for Newtonian fluids. For non-Newtonian fluids, there are more complicated equations, but these are the equations that we are going to develop, as well as we are going to discuss them, discuss different aspects of these equations, develop them, and see their applications also. And in this case, we start normally with developing the equations of continuity. Then we will discuss momentum equation, Euler's equation, and the most generalized form among this set of problems as what we call as Navier-Stokes equation. And then we will also consider applications of the above equations, as well as how they are applied and how the problems are solved by using these equations. And then we will consider the special cases also, because all these equations have different implications, different aspects, different boundary conditions, and all these things play an important role in solution of fluid flow motion, as you can guess. And in fact, you may be little bit familiar with. Continuity equation is basically the conservation, what we call as reflecting the conservation of mass. The momentum equation reflects the conservation of momentum. Euler's equation is an equation of motion that reflects the momentum equation, but for kind of real fluids, and we assume for ideal fluids, in which we consider as if we are considering a fluid flow in which there is no viscosity. Now, normally it does not happen. All real viscosity will have some value, and if it has some value, then viscosity is there. So we cannot say a fluid is non-viscous. But what happens is that the viscosity is so small compared to the other forces that are acting. For example, there is velocity, for example, there is a force, acceleration, the time variation, and similarly other things. And therefore, the viscosity, therefore, compared to those forces, can be ignored, and we can safely assume that in an ideal flow, there is no viscosity. And we have also seen that in cases such as that, and we will discuss them when we come to it, that the results obtained from the solution of Euler's equation is quite realistic. They matches the real situation, given that the conditions that has been assumed are also met in those cases. Navier-Stokes equation is a general form of equation in which all forces, particularly the viscous forces, are considered and they cannot be neglected. But the problem with Navier-Stokes equations are they are nonlinear equations, and nonlinear equations are difficult to solve. To the extent that till today a unique solution to these equations have not been obtained. So we only obtain somehow simplified or restricted solutions under restricted constraints or conditions, and a generalized solution is not available. And then because of this problem, in some cases we consider some of the special cases that pertain to this, the application of Navier-Stokes equation, because viscosity and the nonlinearity that is there in the equation plays an important role and makes it difficult to solve. And to solve it, even a lot of use of computational methods is also used, using finite element methods, and other computational techniques are used to solve very complicated problems, and they have produced good and useful results. The equations of fluid dynamics, the physical meaning of the terms in the equations of fluid dynamics. So every term that is involved there, we have already discussed it so many times that I don't think we need to go over it again. For example, that a fluid will have mass, it will have density, there will be time definition, and so on. And then they are derived from the basis of the very well-known Newton's second law of motion, known as F is equal to ma. The force is equal to mass into acceleration. And from that, the governing equations of motion are derived. The fluids that follow Newton's law, that work under F is equal to ma, they are known as Newtonian fluids. The fluid and most fluids follow under this category. But there are non-Newtonian fluids where the Newton's law is not applicable. Newton's second law of motion is not applicable. And the example of this is, for example, in elastoplastic material, like in paste, then they are fluids and not fluids, and somehow if the forces are applied, then the force is not proportional to acceleration, and therefore the Newton's law is not for, and therefore different techniques are used to solve them. For the moment, we are not considering that. We are considering only those fluids, that kind of fluid motion which follow Newton's laws of motion. We talk about the control volume analysis. When we are considering a particular fluid flow, then of course we can't cover the whole fluid flow area where it is moving. So we pick up a typical volume of fluid that typically represents the fluid. Now there are two types of things that the way we can attack this problem. One is by choosing the control volume, and the other is by controlled surface.